Okay, so the idea is to have a matrix and to try to find the Jordan form of this matrix. Not just that we'll find the Jordan form of this matrix, we will also find a matrix, let's call it P, such that this P will be the transforming matrix. So here we have A, this is the matrix that we will transform into its Jordan form. And we want to find not just the Jordan form G of A, but also P such that inverse of P, AP, will equal the Jordan form. So let's start with finding the characteristic polynomial of A. So this is the way to find the characteristic polynomial, and this is the result. We have an eigenvalue of 2 with algebraic multiplicity of 2. Now if we look on the eigenspace of this eigenvalue, we will get that the rows are linearly dependent. So the rank of this matrix is 1. Therefore, we have only one eigenvector for this eigenvalue, namely the geometric multiplicity of this eigenvalue, lambda equals 2, is just 1. We have only one eigenvector that is related to the eigenvalue 2. So of course, this matrix is not diagonalizable as the algebraic multiplicity does not equal the geometric multiplicity. But of course, we have a Jordan form because the characteristic polynomial is built from linear factors. So what will be the Jordan form? The geometric multiplicity tells me how many blocks I will have from this eigenvalue. So the geometric multiplicity is 1. Namely, I will only have one block from the eigenvalue 2. And this is my only eigenvalue. Therefore, the Jordan form will be built only from one block corresponding to the eigenvalue 2. So this is it. 2, 2, and above that 1. This is one block, size of 2, for the eigenvalue 2. This is the Jordan form of A. Now we want to find the P matrix that will transform A into its Jordan form. This invertible matrix P such that the inverse of P times A times P equals the Jordan form. Now for diagonalizable matrix, what we are doing is using the eigenvectors, because for a diagonalized matrix, we have a base of eigenvectors. We put them as the columns of P, and this P will diagonalize the matrix. But now we don't have a base. We don't have enough eigenvectors. We only have one eigenvector. And the dimension, of course, is 2. This is a 2 by 2 matrix. So we will do what is called generalized eigenvectors. But let's start by finding one eigenvector for the eigenvalue 2. We will solve the equation a minus 2iv equals 0. This is it, and solving it will give me a vector that its x component should be twice its y component. So for example, I can take this simple vector 2, 1. This will be an eigenvector for the eigenvalue 2. But we need another eigenvector, or we don't have another eigenvector. So we will find a generalized eigenvector. And we'll call him v2, such that a minus 2i times this generalized eigenvector will be equal the eigenvector we really have. Now solving this equation, a minus 2i is this, v2, let's call its x component a and its y component b, we will find them, and v1 we found. This is the 2, 1 we found. This is the eigenvector. Now let's solve this system of linear equation that we are getting. And what we are getting is that a should be 1 plus 2b. So if we define b to be 0 and 1 to be 1, and a to be 1, we're getting this v2 instead of a1 and instead of b0. So now we have v1 and v2, v1 and v2. We will put them as the column of the matrix P, and using this P, we will be able to do exactly this, to transform our matrix into its Jordan form. So let's do it. Here it is. This is P, and this is the result. We will even be able to see exactly the calculation This is for P minus 1 using the adjugate matrix formula for finding the inverse, 1 divided by the determinant of P times the adjugate of A, which is this one. This is the inverse of P. So calculating it, we are getting really the Jordan form of A. So that's all. All we did was taking the matrix A, finding its characteristic polynomial, leaning on the algebraic multiplicity and geometric multiplicity, seeing that it's not diagonalizable, the geometric multiplicity is less than the algebraic multiplicity, finding by that the Jordan form, wanting to find the transforming matrix P, so finding the generalized eigenvectors. After finding the eigenvector, by these vectors we are building the P, finding the inverse of P, and coming to this result that this is exactly what we wanted. So thank you all very much. This was about it, finding the Jordan form of a matrix and its transforming matrix P. And also, we saw a little bit on generalized eigenvectors. Thank you all very much. Thanks for Copilot for writing it down. And that's it for now.